Thank you. Yeah, thank you. Yeah, so today I'll be presenting sort of a large portion of my thesis work. I'm a fifth-year student now, so I have one more year before I graduate. And hopefully by the end you'll be convinced that, we need to point the world's most expensive telescope at these weird objects. And so to start out, maybe. Oh no, is it working now? Oh yeah, maybe click it. Okay. So first I'll start off with why does anyone need a $10 billion telescope? I'll talk a little bit about the universe's expansion and what does it mean for the universe to be expanding. I'll talk a bit about how our measurements could be wrong. And then I'll show how JWST will come in and save the day. I'll talk a bit about these weird terms, so strong lensing and quadruply imaged quasars. What are these objects? And then finally, I'll finish by presenting a sort of state-of-the-art measurement. So after decades of work, what value do we get? And so next, yeah. And so why does anyone need a $10 billion or 1.5 trillion yen telescope? So next. And so the key here is that the sort of reasons why JWST was able to get this much money was to answer these sort of fundamental questions that is sort of natural to the human condition, right? So what is the universe made of? Are we alone in the universe? And my favorite question, which is next, will we all die a lonely death, right? And so this will require quite a bit of work to do. Can I maybe see the... Oh, maybe this is falling out here. Maybe? Oh, sorry about that.
Okay, it's good now.
Okay. Okay. And so next. And so what does it mean for the universe to be expanding? And so typically when people think about the universe expanding, they have this picture of, there's a single point, and that single point is now expanding into sort of empty space, right? And this is a bit of a misconception. So the universe doesn't start as like one singular thing that grows into nothingness. A better picture is that the universe sort of starts what we think is infinite, and then actually the distance between any two points is growing. And so this is a sort of misconception. And the next. And so maybe a better example would be if you imagine, on the weekends, you're making some raisin bread with your friends. And so you have this raisin bread dough. And you can imagine the distance between the raisins before it rises is, some distance apart. And then you can imagine after you leave it to rise, after that amount of time, the raisins are now slightly farther apart, right? And so the idea here is that, when the universe is expanding, it's not that, the edge is going into nothingness. Rather, any distance that I'm sort of holding is growing with time. Okay, next. And so there's a few ways to measure the expansion rate. So one is we can sort of observe how quickly the raisins are moving away from us today. And so you can imagine if we're right here, what we can do is we can sort of just measure, okay, how fast is that raisin moving away from us? And how fast is that raisin moving away from us? And based on that, we can sort of measure how fast the universe is expanding. And so in 1929, this is sort of what Hubble did. So if you've heard of, Hubble Space Telescope, named after this wonderful astronomer. And what he did was he found that almost all the galaxies that he looked at they were all moving away from us. And so in this figure here, we have distance. So, farther away galaxies are down here. And then we have velocity, so things that are moving faster. And so what he found is that on this figure, you can see that the farther the galaxy is away, the faster it's moving away from us, right? And so this sort of makes sense. The farther away that wall is, there's more space between me and the wall. And so all of that space is expanding, and so it's going to be moving a bit faster compared to, me and this table. There's not much space here. And so when it's growing, there's not much expansion going on, right? Does that make sense, sort of conceptually? Yeah? Okay, great. And so when I talk about the rate of expansion, you can sort of think of this line here. And so it's sort of based on what distance, how fast am I going, right? Okay, next. And so there's a second way to measure this expansion rate. And so let's say we have like this incredible computer that knows everything about bread dough, right? And so let's say I give it a picture of my bread dough initially, and it can sort of predict how it's going to expand in the future, right? Does that make sense? And so let's say I have a really cool picture of my bread dough initially. I can sort of feed in my model of the universe. And so this will be sort of what I call the standard model. And so the standard model is sort of what most cosmologists have been using for the past few decades. And it's been able to prove a bunch of really interesting predictions for the universe. And so plugging this picture of my dough into this standard model, we can sort of see what we should be seeing today. So next. And so this was done with data from Planck here. And so what you're seeing here is essentially the first light of the universe. And so if you imagine, looking out past the moon, and then, past the sun, past, the closest galaxies, past the farthest galaxy, and then past, the very first star, all the way past that, eventually you'll see this sort of wall of light everywhere. And so what you're seeing is sort of deformities in that wall of light. And so we can't really see past that. And so this is essentially our picture of the dough or the very early universe, right? And so if you have this really cool calculator or, theory of the universe with the standard model, we can sort of take this picture of the early universe and then compute what the expansion rate should be today. Next. And so here we have, these two ways. So first we can observe what we see the expansion rate to be today, and then we can compare that to how we predict the expansion rate should be today based on those early universe observations. Next. And so why is there so much drama, right? So the first measurement of the late universe, so again, this is what we see when we look out, is in blue here. And then I'll compare that to the early universe, so what we expect based on our model is in black here. And so, early on in 2001, we made our first measurement for the late universe, and we got, the expansion rate in some units. And then a couple of years later, the early universe, we're like, okay, this is what we predict the expansion rate to be. They matched perfectly. This is another breakthrough of the standard model. Everything is perfect and solved. And so they continue working on, let's see how tightly we can measure this expansion rate. And so, 2010 comes around, and they're like, uh-oh, it's still pretty close. Maybe things aren't totally wrong. Let's continue working and see what we find. And then around 2020, it's sort of, a bit of a disaster, right? So what we actually see the universe expanding is much higher than what we actually predict the universe to be expanding at. And so this is sort of known as the Hubble tension, right? So there's this tension between what we actually observe and what we predict the expansion rate to be today. And so this is a very big disaster sort of in cosmology. Next. And so the summary of sort of the state of the art today is that we really don't know why the universe is expanding so quickly. And so where are we today with these measurements? And so here's sort of the current status. And so again, on this bottom axis here, I have the expansion rate. On the top, I have those early universe measurements. So if we give it that picture of the early universe and then see what we predict, we get these values over here that are smaller. And if we look out at the late universe today, we get these sort of different values here. And I've hidden a result that I'll go over later. And so you see there's this sort of tension between the two. And at this point, it's about 5.6 standard deviations away. And so to put that in perspective, it's more likely that could it be just random statistical chance? And so one thing that you can do is you can imagine I grab a coin, which I have in my pocket. And so it's more likely that if I flip this coin, 1 second. Okay, I got tails. And so next slide. It's more likely that I flip the coin and get tails. And if you go to the next slide again, flip it, getting tails again. Tails one more time. Actually, the next 10 times I flip the coin, they're all tails. And that actually happens like twice in a row, right? So it's more likely that you flip the coin 26 times and they all come up tails. And so the consensus we have is essentially that, it's probably not just statistical chance. And so then the next approach is, the sort of conclusion that we have is either our measurements are wrong or our understanding of the universe is wrong. And so there's this big question of, which one's the issue. And so one thing I wanted to point out with these measurements of the expansion rate is that this axis down here is very hard to measure. So distances. So you can imagine, if you go to the next slide, on Earth, if I asked you to measure distance, it's very easy. You could pull out a tape measure. And so if I wanted to know, what is the distance from me to the wall, I could pull out a tape measure and measure, it's 15 feet. Sorry, 5 meters. Meters, apologies. 5 meters away, right? It's one of the easiest things you can ask. But if I show you a picture of a bunch of galaxies, here's JWST and here's HST, and I ask you the question, which of these galaxies is the farthest? It's a much harder question, right? And so if you are clever, maybe you'll say, oh, the smallest one is probably the farthest. But then you know that some galaxies are just smaller than other galaxies, and so that doesn't really help. If you have a bit of an astrophysics background, maybe you see the reddest one is probably the farthest away due to something called redshift. But some galaxies are redder than other galaxies, and so that doesn't really help us either. And so maybe you're very clever and you say, okay, well, you can take a spectrum and you can figure out which one's farthest away, and sure. And so maybe you find out that it's this galaxy that's right here, right? You can't even see it in HST. And so sure, that's fair. The next question I would ask is, how far away is it? Any ideas on how you would measure the distance to that galaxy?
It's kind of far.
It's pretty far, right? And so there's a big challenge of measuring these distances, right? So when I talk about the expansion rate, that x-axis was the distance. And so how do you measure these distances is a very, very challenging question. And so what these sort of late universe probes do is they use something called a distance ladder, which I'll explain here. And so, for example, how far is the Hollywood sign from my house? And so on the bottom left here, I have a picture of one of my cats in a box, as cats tend to do. And then over here, I have the Hollywood sign. And so if I wanted to measure how far the Hollywood sign is from my house, I would start off by maybe measuring one step of mine is 1 meter long. Sure, doesn't get me all the way. And then maybe I walk a block, and I find that 200 steps are in a block. And so that gives me, 200 meters. And then finally, maybe I measure, there are 100 blocks to the Hollywood sign, so that'll give me, 20 kilometers. And the distance from my house to the Hollywood sign is actually 24 kilometers. So this is actually a pretty close approximation, right? And so the idea of this ladder is that you're starting off with, some small step. That small step builds your next steps, and you sort of make up this ladder of going from a small distance to build up a larger distance to build up the largest distance, right? Does that make sense? It's a sort of ladder, right? And so there's one concern that if any one of these measurements is wrong, your entire estimation is going to be wrong. If I mismeasure, the distance of my first step, my distance for all of these blocks are going to be wrong, and my distance for the total distance is going to be way off, right? And so this is a very sort of precarious way of measuring things. And so what I propose is, what if we just try to measure one distance from my house to the Hollywood sign using a very special ruler instead? Will we get the same result? And so if you remember that figure I showed before, that gray bar, this gray bar here will be, what if we use no distance ladder? What if we just measure one direct distance? Are we going to get the same result, or will it be different? And so what is our special ruler? So if we're using one ruler to measure these distances, and I'm measuring, the expansion rate of the universe, that ruler has to be, pretty damn big, right? It has to be a massive ruler. And so we have to be able to see things that are extremely far away. And so we're going to combine 3 different ingredients to see very far away. So first, we're going to use the most sensitive telescope ever built, which will be JWST, as we've already seen. Second, we're going to use quasars, which I'll explain later. They're the brightest objects that we know of in the universe, which lends themselves to be seen from very far distances. And then finally, we're going to use strong lensing. And so strong lensing acts as sort of like a magnifying glass. And so if you wanted to see something very far away, maybe you use like a magnifying glass or some sort of telescope to zoom in on those objects even farther away. And so first, the telescope that we're going to be using is JWST. So the typical saying that people have is that it's sensitive enough to detect the heat of a bumblebee on the moon, which is kind of crazy to think about. It launched in 2021, and it's had a sort of revolutionary effect on many fields in astrophysics. And so next, what are we going to be pointing this telescope at? We're going to be pointing them at something called quadruply imaged quasars. Kind of a word salad, and so I'll go line by line. So first, what is a quasar? And so here are some pictures from JWST of some nearby galaxies, so not the ones that I'm going to be looking at. And you can see all of this amount of structure in them, which is very cool. And one thing that you'll notice is that some of these galaxies have this very bright object in the middle, right? And so this bright object in the middle is sort of a very weak version of the quasars that I'm going to be studying. So you imagine if this is 100 times brighter, right? These would be the types of galaxies that I'm looking for, right? Next. And so if you've seen the movie Interstellar, what you can imagine that object is at the center of those galaxies is a supermassive black hole. And near that black hole, there's this thing called an accretion disk. And so you can imagine it's sort of space dust. Technically, it's gas, not dust. But it's going around extremely quickly, right? And so you'd imagine black holes are very heavy. And so if you want to do an orbit around that black hole extremely closely, you're going to be going very fast, right? Like almost the speed of light. And so you're going to be bumping up against a bunch of other gas that's also trying to orbit at the same time. And so you can imagine if you try to like rub your hands together like very quickly, you'll start to heat up and feel some friction. And if you rub your hands together, almost at the speed of light, you'd feel a lot of friction. And so that's how you get this sort of heating effect, which causes it to be extremely hot. So next. And so this accretion disk can be up to like 300 million degrees Celsius, or about 50,000 times the heat of the sun, which is kind of a lot of heat. And from that heat, that's how you get this sort of glow. So if you have like an electric stovetop, as you heat up that stovetop, it starts to glow as it gets hotter and hotter. You can imagine if you're 50,000 times the temperature of the sun, you're probably glowing pretty brightly. And so that's how these things become the brightest things that we know of in the universe. All good so far? Does that make sense? Okay, great. So these are quasars. And then next, what does it mean to be quadruply imaged? And so this relies on something called gravitational lensing. And so the idea here is that, typically when we think of light, it sort of travels out in straight lines. But what you'll see is if you have a very heavy object, it actually bends space-time around it. And so instead of traveling in these straight lines, what you'll see is that the light rays will actually bend around the object itself. Right? Can everyone see the animation? Am I in the way? And so you can imagine if we were, placed around here somewhere. On the next slide. Let's say Earth is placed, sort of right here. What we look up and see on the sky is that there's a light ray coming from this angle here, and there's a light ray coming from this angle here. But they're coming from the same object, right? And so next, what we'd see on the sky is that it would look like there's a quasar over here. It would look like the galaxy's in the center, and it would look like the exact same quasar is on the top. So this is one object, but when we look up on the sky, it looks like there's two of the exact same object on either side of this galaxy, right? And so that's what it means to be multiply imaged. Okay, does that make sense? Okay, great. And so here's a little simulation showing what I mean. And so on the top left of the simulation, I have a sort of like unlensed image. And then in the main screens here, I'm sort of lensing that by masses of different shapes. And so what you see is that this image is sort of being bent and distorted into different shapes. And so when it's farther away, you can see it's sort of stretched out vertically. And as it gets closer, you get this sort of stretching, and it sort of turns into a ring. And keep in mind, these four images are this one object. You're seeing it 4 different times. It's all coming from the same object. But it looks like there's 4 of them, right? And so, okay, we're looking at these quadruply imaged quasars. The whole point of me telling you this was to somehow get a distance. How am I getting this distance, right? The whole point of this, to measure the expansion rate of the universe, to do that, we need to measure distances. Where's the distance coming from? And so the whole joke here is that whenever anyone presents you a late universe expansion rate of the universe, it's really just how they measure distances to a very large scale, right? And so again, if we go back to this picture here, let's imagine the Earth is placed here. Can we all see? And let's say there's a light ray coming this way and a second light ray coming out that way. What you could see is that here are the light rays, and then let's say this quasar sort of like fluctuates in brightness, so it like flares up momentarily. What you'll see is that flare up has to travel through these light paths, but light can only travel at a fixed speed, right? It travels at the speed of light. It doesn't travel instantly. It has to go through that entire path. And so what you'll see on the sky is, over time, it sort of travels farther and farther and farther until eventually one will hit us. And so you see a flash in one image, but you haven't yet seen it in the second image. And so what you can do is you can start a stopwatch, right? And you can see how long does it take before I see that same flash in that other image that I see, right? And so you can imagine I have two pictures here. So this little unit here is called the sort of like time delay. So it's how long it takes for that second image to sort of flare up. And so let's say instead of having that geometry, which is very big, I have this one here, which is the same thing, just slightly smaller. And so let's say light had to travel this path instead. What do you think would happen to the time delay if this was my picture instead? So light is traveling this way and this way. This unit of length is a lot smaller than this unit of length, right? And so my time delay here would be a lot smaller. Does that make sense? Right, so if the quasar is closer to the Earth, this time delay is going to be a lot smaller, and so light can hit us, very soon after this one hits, whereas that one would take a lot longer to hit us. And so the idea here is that the smaller this distance from the Earth to the quasar, the smaller that time delay is going to be. And so, on the contrary, right, if you can measure this time delay, you can get some information about what this distance is. Does that make sense? Yeah? Okay, great. Yeah. Oh, yeah?
That's providing you know the distance of the thing that you're lensing around. Is that correct?
To some extent,
okay.
Yes. There are some approximations that you can make, but yes. It relies on, the relative distances of these objects, yes. Yeah. And so next, if you remember this sort of picture here, where we had the distance ladder, where you measure, one distance, then from that distance you can build another one. We no longer have to use that distance ladder, right? No longer needed, because now we're able to measure one distance in one big step, right? So based on this time delay, one big distance. Great. If there are any issues with the distance ladder, they would no longer show up in our measurement, is what we're hoping, right? Okay, great. So awesome. We get some sort of distance from these quadruply imaged quasars. What do they actually look like, right? And so next, I'll show some pictures from HST. And so here are those quadruply imaged quasars. So the quadruple, you can tell there are 4 different images here. 4 images, 4. Is this a 4 image?
Yeah,
okay. And then here, the 1, 2, 3, 4. And so what you're seeing here is, if you go next, so this ring is surrounding this galaxy here, right? You see the galaxy in the middle? So that's like the deflector galaxy that's bending space-time around it. And this ring is coming from a galaxy that's behind that deflector galaxy. So in this picture, there's 2 galaxies going on here. There's this one in front, then there's one behind. And the one behind is getting its light bent around into that ring. So if you remember that animation that I showed you, this is the thing in the background going through that bent space-time, and we're getting this ring structure. That's exactly what you're seeing here, is that ring structure. All right, all good? And so the next, these sort of 4 bright objects, that was that quasar. Right, does that make sense? So you have a very bright object in the center, that's being here, and then all of this junk around it, all of this sort of yellow ring-like junk, is all of this stuff around the quasar in that background galaxy. All of these sort of arms, all this sort of substructure is being bent around into this ring. Does that picture make sense? Yeah? Yes?
Just one question.
Yeah.
Okay, so it's the smaller parts that basically we have 4 different images
Yeah.
that are kind of similar.
Yep.
Okay.
Yeah, exactly. Yeah. So here we'll actually get like 4 different, well, I guess 3 different time delays, right? One from each of the images. And then you can compare them between each other, right? 3 independent time delays, I guess. Yeah. And so next the question is, those are pictures from HST. So what can we see with JWST, right? So going to the next telescope. And so here's the HST picture of the system that I was modeling for 2 years. And so next, this is the sort of enhancement that we get with JWST. And so previously, this ring-like structure on here was barely visible. And that ring-like structure is like the most important thing we need for these measurements. And so going from HST to JWST, you see this sort of full like ring-like structure. You can even see a little bit of substructure, so this sort of clumpiness that maybe you can make out. You get a really nice image of this sort of satellite galaxy on the outside. And so these offer really nice constraints on these measurements of distances, right? And so going from HST to JWST is a huge improvement for these distance measurements. And so yeah, I spent a very large portion of my life modeling this one image. And so this image, I have probably spent hundreds of hours of my life looking at just this image, right? A lot of work. And so this is what we actually observed. This is the observed image. Here's my model. And so this is what I was able to reproduce just using math, pretty much, to sort of figure out the whole geometry of that system. And then here's sort of how off my model is. This thing right here is the source galaxy. So remember there's 2 galaxies. There's one in front, one in behind. This is all of the detail in that behind galaxy, right? So you can see it almost looks like there's maybe arms. There's like this clumpiness going on. And so this is all detail that we're able to make out from an extremely far away galaxy that holds that quasar in the center. Does it all make sense? Great. And so what do we get when we go from HST to JWST? What we find is a total overall sort of modeling improvement of about 22%. And so that distance measurement, is improved by about 22% from the modeling. And so here, we're sort of increasing the amount of information that's going to the model. And so, this is the big payoff right here. And then on the bottom here, we essentially have, some proxy for the expansion rate, right? And so what we find is that it's sort of still consistent with the HST results, but those uncertainties are, about 22% tighter, which is great news, right? And so each of these systems is going to be combined together to form our measurement of the expansion rate, right? So we're observing multiples of these systems. We're modeling all of them, and each of them are giving us a different measurement of a distance. From that distance, we can get an expansion rate, right? And so we're combining all of them together. Does that make sense? Great. And so JWST is helping tighten those uncertainties by quite a bit. And so here are the HST images, so the previous, flagship space-based model. And what you'll see with JWST is that we're making out an incredible amount more detail, right? So you can see in this ring structure here, which is pretty visible in HST, I'll give it that. Down here, you're able to make out, individual sort of clumps. These we think are star-forming regions in that background source galaxy. You're able to see sort of star-forming regions within the actual spiral itself, and then some that are a little bit farther away from that center of the black hole. And I mean, as you go off into different bands, and so these are different wavelengths that you're looking at, and so this is redder and this is bluer. In these redder wavelengths, you'll see like almost a complete ring, which before we didn't really have, right? So similarly, down here, we have another case where there's barely any ring-like structure. And going across here, you see an incredible amount of ring-like structure. This is super important for those distances. And so we actually just got approved for observing 10 brand new systems that have never been used for time delays. And so this is more than doubling our sample size, which is really exciting. And so we're hoping to really narrow down those uncertainties over the next year or so. All right, and so what's the big reveal? So maybe I'll do a quick recap before I reveal anything. So why do we need a $10 billion telescope? Kind of a lot of money. we don't really know what the expansion rate of the universe is. There seems to be some sort of tension between what we predict and what we observe. It's very hard to measure distances in space. And so with this new telescope, we can get tighter measurements of distances. With these distances, we can get tighter measurements on the expansion rate to sort of figure out, is our theory correct and our measurements are wrong? Or are our measurements of what the universe is expanding like today correct, and our theory over the past 2 decades, is our theory been wrong? And so what we find is that, okay, almost there. And so what we'll find is that, completely independently of these late universe measurements, what we find is that our results are consistent with what they're observing today. And so it seems like the cosmological model that most people have been using for decades is actually wrong. There's something missing, and we don't know what it is. And we're hoping with 10 new systems with JWST, we can get really tight constraints on what that missing parameter is and how we can constrain that missing information. So yeah, thank you so much.
Thank you, Devon.
Oh, yeah.
Thank you for a great talk. So we have some time for question and answer. So please raise your hand and I will call on you. And please wait for the microphone. So Stephen will give you the microphone if you have questions. Yeah, right there.
Thanks for the talk.
Yeah, just speak into it. It's for the video.
Yeah, okay. So yeah, thanks for the talk. I have a question about the quadruply image process.
Yeah.
Why are they quadruply imaged? So,
Yes.
Because when you showed the deformation on the plane, I guess it's rotated all around the closest galaxy. So why do we not have this bright space all around as well, and instead we have these clusters?
Yeah, so why is there a gap in between the images? So if I go back to why is there a gap between these images here?
Yeah, exactly. Like, why is the bright light not reflected all around the object?
Yeah, so that's actually a really great question. And so what I'm showing here is that different geometries of that lensing galaxy that's bending the light will bend the light in different ways. And so here what you're seeing is if that galaxy in between you and that sort of quasar, that galaxy is a perfect sphere, what you'll end up getting is that perfect ring, right? But let's say that galaxy in the middle, you stretch it out vertically, and so now it looks sort of like an oval like this, a really tall oval, right? You're no longer going to get a ring. What you'll get is that ring will sort of split. And so what you'll see is, these 4 independent images rather than that full ring-like structure. And what causes that is that because this deflector galaxy in between you is more elliptical rather than spherical. And so you don't have that many axes of symmetry, if that makes sense. So it's based on the number of axes of symmetry. And so you can imagine if it's a perfect sphere, you can go across anywhere. But if you have an oval, you only have vertical and sideways, and so you get the 4 images. Does that help? Yeah. Okay, perfect. Thanks.
Right.
Thanks. Yeah, sort of following up on that.
Yeah.
Because I was, for the measurement method, you were saying that you measure the time delay between the different points.
Totally, yeah.
And later on in the talk, you were saying how getting the ring structure was really helpful.
Mm-hmm.
And I was sort of struggling to get my head around how the ring structure helps when you were originally looking at the different points. And yeah.
Yeah, that's another fantastic point, actually. And so the ring-like structure actually helps you constrain sort of this shape here. And so there are a few options. So this is like, imagine you have like a full sort of large elliptical shape. There's another option where it's sort of that mass in the center. There's like a bunch of mass in the center and it falls off very quickly. You also have the case where maybe it's evenly distributed along that oval. And so those are 2 different cases that will have 2 different sort of time delay predictions. And so if I show you this model here, sorry, thank you, yeah. If I show you, yeah, I think this figure will help. So essentially, if you imagine this galaxy is like has a bunch of mass in the center, this picture that we draw here is going to change. You know, this line might move in a little bit. This one might move out a bit. Compared to the case where maybe this galaxy is like very flat, it has the same mass everywhere, then maybe these will, this one will move in a bit and this one might move out a bit. And so based on that ring-like structure, we can figure out whether it's flat or whether it's sort of steep in the middle. And that helps us constrain this picture here, because that'll move this picture around.
So it's like to understand the shape of the original galaxy that you're taking the measurement from. Yeah.
Yes, yes,
Right.
yes,
You're
yeah.
still measuring from the center point, I guess, where the quasar is for your measurement, and that's why the points are important.
Yes, yes, exactly, right? Yeah, yeah, totally.
And sorry, so you measuring quasars,
Mhm.
but the lensing is a galaxy, or can that be a quasar as well, or is there too much
Yes.
detail, or- I'm just
So I believe there is at least one, I think one has been observed, where you have a galaxy containing a quasar lensing another galaxy containing a quasar. I believe there is at least one system that is
Might be a
known.
I'm not sure about that actually. It could be quasar galaxy, not quasar quasar. But
Oh, it could be quasar galaxy, yeah. I think there's one, but if there's not, scratch this from the record. You know, I'm not.
But it doesn't really matter so much. It matters that you have something to provide the lensing, and you're taking the measurement from the quasar.
Yes. So the main value of this picture here is that this thing sort of fluctuates in brightness, and if this thing fluctuates in brightness, then we're able to get this time delay. So if you have like a galaxy and like a regular galaxy here, you'd run into this issue where like galaxies don't really change in brightness that much, and so you wouldn't be able to measure a time delay because your images will just always look the same. Like nothing interesting would happen. Whereas quasars, you know, sometimes a star will fall into the black hole and it sort of flares up in brightness, and so you can measure this sort of time delay. Does that make sense?
Yes. Thank you.
Okay, awesome. Thank you.
you over here?
Yeah.
One question is
Mhm.
just following on the same subject.
Mhm.
Is the shape of the quasar galaxy
Mhm.
having an impact on the calculation,
On the what?
on the entire operation? Because
Yeah.
we were talking about the impact of the lensing galaxy. But
Yeah.
The galaxy being lensed
Yes.
also
Yeah. Yeah.
can have different shapes.
Yeah, totally. So if I show you this picture, so if we look at the different systems, maybe this one is good. So let's compare, for example, you know, this case here and this case here. So in this case here, that background galaxy, we're able to make out, you know, a lot of different structure here. You can see, you know, there's a dark spot, there's a bright spot, there's different clumpiness and chunks here, right? Whereas here, it kind of just looks like a circle, right?
Yes.
There's not much going on here, right? And so the more detail that we can make out in the source structure makes it a little bit easier to sort of answer the same question that was asked before, where we're trying to figure out how much mass is in the center, how that mass falls off, because that sort of changes the lensing picture. If you have a lot of structure like this, it can help constrain how that mass is falling off from that galaxy in the middle, right? So if you don't have, you know, if you just have a ring, you know, it's good enough to get what you need. But if you have a lot of this structure, it gives you really tight constraints on how this mass is sort of changing with radius. Yeah. Does that answer your question?
Yes.
Okay, perfect. Thanks.
Over there. You go.
My question would be how big or how long is the time delay, and
Yeah.
how long do you expose
Mhm.
the image, and how long is the exposure time as compared to the time delay?
Yeah. I'm not sure about HST exposures. Like typically,
For the time delay, it's ground based.
yeah, the time delays are ground based. So essentially, we'll be monitoring them for like decades, right?
Oh, okay. So you're monitoring the brightness of the quasar, and then
Yeah.
so you're pointing pointing at one of the image quasar and then the other
Yeah,
one,
so-
and then comparing the phase difference to measure the time
Yeah, exactly, right? So you don't actually have to observe one and then the other. You can actually just, yeah, you can sort of just, if you imagine like this is my telescope, I can sort of just get all of the images all together. And you imagine if I take this picture, today, tomorrow, the next day, and I do this for a decade, right? I can figure out when one of these images is slightly brighter than the other. And so that's for like decades, yeah.
Okay, yeah, thanks.
Yeah, of course.
Question there?
A little close to the previous question.
Yeah.
I'm sure I may have missed it. Two questions. But first, how much time does it really take for like a quasar to pass across like a galaxy, like a total time? And
Oh,
also,
man,
how do you,
okay.
Like maybe like you start like it's kind of like 1, 2, 3. But let's say that you suddenly have these images with 4 quasars.
Yeah.
How do you tell like the tiny difference between each of these images, or like how should I say of these?
Like, how do you tell they're from the same object?
Yeah. How do you like judge the difference of like the?
Exactly, right? So,
It needs to come to Earth.
yeah. So I guess is your question like, how do we tell that they're the same object and not like 4 different quasars?
I mean, how do you judge like the difference between like each
Mhm.
of these optical illusions?
What do you mean by the distance?
I mean like the time difference. Like,
Oh, the time difference,
yeah.
right. Yeah, so essentially, I guess maybe similar to the last question. So we'll just point a telescope at this for like, just point a telescope at this for like 25 years. And then eventually what we'll see is, one of these images will become very bright for a moment, and then maybe it'll be like dormant for, 5 years or something. And then because we're observing it for 25 years, eventually we see the other one flare up, right? And so we're able to like over 25 years, you kind of just get a lot of data. And you're sort of able to match what these time delays are between all 4 images. I'm not sure if that answers your second question, maybe.
I think at least I have an idea. So also
Yeah.
it's around a couple decades, like for average quasar to completely cross like a galaxy.
Yeah, to completely cross.
I mean, to like
We-
appear as like one star again.
What was that?
I mean, like I think previously from the Earth it was once was like one star, but then it split and then it will become one star again. But how much time?
Oh, like in my simulation, like it was 1 and then went across. Totally, yeah. Okay. So yeah, if I go back, okay, maybe we'll get here. Yeah, so in this simulation I showed you, it started off as one object, it moved, it split off. Okay, great. Yeah, so unfortunately we don't live long enough to ever see something like this, which is really sad. Like I wish we could see something like this. It's really cool. But we would maybe see like one, like, I don't, trillionth of 1 second of one of these things. Like we would never be able to see like a full galaxy move across this sort of distance, unfortunately maybe in like the lifetime of humans. Like if you started with the first human and you had a telescope pointed and you ended with the last human, I don't know if we'd ever see
I think it's
a
off by
crossing.
several orders of magnitude.
Yeah, probably, yeah. Yeah, but I wish, that'd be really cool. What you do see though is, okay, I don't have a simulation here. What you can see is actually like, micro lensing. And so this is the object that like, so here in this picture here, I have like a galaxy. But one cool thing that can happen is, let's say instead of a galaxy that's bending the space, I can actually have like a star. And so this effect is obviously much smaller. But if you're observing something like, I don't know, like a galaxy that's relatively close to us, and maybe a star passes in between us and that galaxy, what you'll see is that star will actually like make that galaxy brighter because it's having this, it's having that ring-like effect, right? Which is sort of magnifying it and making that galaxy brighter. And so, stars can move pretty quickly in our field of view. Galaxies, just because they're so far away, don't really move, unfortunately. Yeah. But you can see it with stars, which is super cool. Yeah.
So
The microphone.
just for Dominic, So we are talking to millions of years or...
For like a galaxy to move. I don't know if like in multiple. It would be of order billions of years. Like a fraction of like maybe like a tenth of the lifetime of the universe or something like that, if not longer.
It might be a little short. I'm not sure, but I think it could be like tens of millions.
Tens of millions? Okay.
I'm not sure. I don't think it's a billion.
Okay. Tens of millions. Apologies.
Okay.
Mark that. Mark that from the record.
Back there.
So you said you've just been approved to observe 10 new quasars.
Yeah.
Does that mean your PhD thesis will last for the next 25 years?
Thankfully not. Thankfully not. It's looking like I have one more year, which is great. So the hope is that as this data comes in, I will be sort of neatly positioned so I can sort of get a postdoc and then analyze that data as it comes in. Would be the goal. But I'm still like, a few months out from applications and stuff. So we'll see. Hopefully I'll have a nice cushy position to be, analyzing those systems. So we'll see. Yeah. Thank you. I might need it.
So maybe we have time for one more question. Yeah,
Thank you very much. I got some question that's
Yeah.
a little bit unrelated,
Sure.
but this is kind of related to the expansion.
Yeah.
Because when I was a kid, I learned that there's a thing called Big Bang and there's a thing called Big Crunch. Because
Yeah.
expansion, there's a limit of expansion and it will start to crunch on itself.
Mhm.
The universe will start to crunch on itself.
Yeah.
But now what I've been hearing from Ken and from you is that the universe keeps expanding and
Mhm.
the model shows that the expansion rate is faster and faster. What are the theories that defeats the theory of Big Crunch?
Yeah. So, so the idea of the big crunch is that, the universe would be expanding outwards. The rate of expansion, it would sort of slow down, and then eventually that expansion would reverse, right? And so the universe starts shrinking and shrinking, and then you and I get closer and closer with time, and me and this projector get closer. Everything gets closer together over time, and you can sort of look at the history. I bashed this model quite a bit, the standard model, and it doesn't seem to do everything perfectly. But most cosmological models, even if you don't use the standard model, you're able to sort of look at the history of how the universe has expanded in the past. And that's, it might not line up exactly today, but, in the near past, they sort of all agree somewhat. And it looks like the rate of expansion has been relatively steadily increasing and sort of slowing down a little bit now. And so it doesn't look like there's any sort of trend to sort of reverse that acceleration. So I think the big crunch is sort of not really believed anymore in most cosmological circles. But that is a sort of like cool consequence of some of these models. Yeah.
Thank you very much.
Yeah, of course.
It was in the 90s, by the way.
Yes.
When I was a kid.
Yeah.
Okay, so I think that's going to be all the time we have. So let's thank Devon again for a great talk.
Thank you.